Hi, thanks for watching this video. This is the presentation that I gave at SEG 2014 at Denver in the booth of Itasca-image. In this presentation, I'll show you the software and the services that we provide to process microseismic data and validate hydraulic fracturing modeling results. The name of the software is called InSite, but we also provide services similar to the software to those who don't have time to learn the software but want to have high-level processing power. Before we start, I just want to keep this big picture in mind. We believe microseismic and geomechanics services should include interpretation and validation. We predict what's going to happen by modeling, and then we update our model from observation, and this learning loop will keep advancing our knowledge of hydraulic fracturing. At Itasca, we provide solutions to hydraulic fracturing and induced seismicity in 3 packages: Foresight for prediction, InSite for monitoring, and Hindsight for validation. This presentation is about InSite, so in the following slides I'll introduce you how InSite can help you process microseismic data or provide you a third opinion in addition to your original contractor. I think we're all on the same page, so I'll go over these slides very quickly. Microseismic monitoring is critical because it provides us a way to look into the reservoir and watch its deforms. By knowing how it deforms, we can increase safety, optimize production, decrease cost, and reduce risks. And all those are valuable to the operators. And to achieve those goals, we need to locate the microseismic events, analyze the spatial and temporal distribution of the microseismic events in terms of the fracture geometry, interpret the results using a fracture network, and estimate the volume that has been simulated. So after all this advanced processing, we can advise our clients, our operators, keep on pumping, you're doing a great fracking job, or the cap rock is not stable, stop pumping CO2. So you see, those feedbacks are very critical and has a long-term impact to the lifetime performance of the reservoir performance. Either your goal is to maximize the fracture network or minimize the fracture network. The concept of microseismic monitoring is simple, as you see in this video. As we inject the fluid into the formation at a large volume and at a high pressure, it will induce fractures and make the natural fractures slide and produce a sound, or just pop up open new fractures and produce a different sound. Those signals will be picked up by a geoform nearby, and we can locate the location of the microseismic events. Advanced processing will tell you if this is a shear event or if a tensile event. So it sounds simple, but along the way, from seismic wiggles to dots in a box, and then beyond the dots, there are many challenges, and simple questions like this have no simple answer. For example, 3 vendors tells me 3 different stories about the same project. Which one should I trust? Well, if it's science, it's supposed to be reproducible, right? But why it's not? Where to put my sensors? How many of them? You want to optimize your survey before it starts. Did I collect all microseismic events? You're not sure if your initial contractor are able to capture all the events. So you want to double check where to start. Can I have a better velocity model? You're skeptical about the velocity model your initial contractor is using, and you want to have a different velocity model to check which one to use, head wave or direct wave. Actually, most of the time is which one am I using, head wave or direct wave. How would that make a difference? One way to check that is to include head wave and then exclude head wave. See if that will make a difference in the location. If it does, you need to go back and reprocess the data. I see a lot of shear wave but no P. What do? This is actually very common. And most locating algorithms rely on both P and S wave to locate the source. So when there's no P, it's a challenge to know where the energy is coming from. The shape, the cloud of the microseismicity forms an interesting shape. Is it real? So you're not sure if your contractor's result is real. I think the best way is to repick the arrival, reprocess the events, relocate, and reinterpret. But what if you don't have the in-house processing power? Then you probably have to contract another vendor. And then it goes back to the question 1. They will tell you another different story. So in the following slides, I'll walk you through challenges like this, and I'll show you how InSite can help you process microseismic data in a reproducible and transparent way. We are not associated with any operator, so the software is available to anyone. Either you just want to have your own independent processing power, or you just want to have a third opinion in addition to your original contractor. Before the service starts, we want to optimize the acquisition geometry, and we provide a solution called Area Analysis Tool. All you need to do is decide the location of the borehole, number of the boreholes, the distribution of the sensor, and the software will show you the 3D distribution of the accuracy or the uncertainty in 3D, as you can see here. And you can change the borehole distribution, sensor distribution, till you're happy about your results. The first example is this so-called misfit space, which is defined as the differences between the theoretical arrival and the calculated arrival. So if this is your theoretical source point, the misfit space will be minimum at the true source location, as you can see here. And this is the error. As you go away, move away from the true source location, the error will increase. So this picture gives you a uncertainty distribution in 3D. If you change the borehole location, add another borehole, change your velocity model, the misfit space will become more complicated than this. The second example is the magnitude sensitivity. So in the region close to the borehole, the minimum detectable magnitude, as you see in this picture, is -4, and when you go away from the borehole, the minimum detectable magnitude is -2. So if a region far away like this is critical, you probably better increase the sensitivity of your geoform or add another observation borehole nearby. The other story I want to share with you is recently we have client asking us, we have two options of perforation shot. One is expensive, but the vertical depth is relatively accurate. The other one is cheaper, but it comes with large uncertainty for the vertical depth. Do we have to go through the expensive one so that we have a better results? The answer is not at all. It depends on the reservoir conditions. In some reservoir condition, the uncertainty from the perforation shot is not going to propagate into the microseismic events. So if that's the case, then why go for the expensive one? So you see, you have a reason to accept or reject the recommendations of your initial contractor of their own technology. Once the survey starts, the data will keep coming and fill up your data hard drive very quickly. And we need a tool to scan the data as quickly as possible and as carefully as possible. To be quick because we want a real-time feedback, and to be careful because we want to capture as many events as possible, which will warrant a good interpretation later on. So the solution we provide is this data management tool, and we call it leaching, or you can call it data capturing. The basic idea of this data capturing tools is to scan the data streams and look for a segment of waveform that is matching the predefined criteria, and you are the one define the criteria. It can be the signal to noise ratio, the amplitude threshold, or the move out pattern. As long as that segment of waveform matches your criteria, it will be saved as a triggered event. And that triggered events can be shared online if you want. So the field engineer can process the results, as well as a remote geophysicist in the office via internet connection. We designed this tool to be hardware independent. So it doesn't matter who is collecting your data. It could be, Slumberjay, ESG, it works the same. And you can use this tool to capture your data, and you can compare if your initial contractor is able to capture those events as you do. So to locate the triggered events, we need a velocity model. And the solution we provide is the InSite has a tool to search within the domain that you defined for the velocity and systematically minimize the differences between the theoretical arrival, the black lines here, and the actual arrival, the red lines here. And once the InSite found the optimum velocity model, the differences between these two lines will be minimized. And all you need to do is to decide how many layers you want and the upper and lower boundaries for each layer. The program will search within the space that you defined and get you the well-calibrated velocity model. If time is critical or you want to add your own velocity model, you can use a manual check or manually change the velocity values, as you can see in this video. First of all, we have a calibration waveform. Usually it's coming from a perforation shot, and we have a theoretical arrival lines here from your initial velocity model, which usually are not optimal. The red lines here are your velocity model, and the blue lines here are the well logs. So all you need to do is change the values for each layer by move and drag the red lines here, and each time you change the value, the theoretical arrival will be updated instantaneously. So you can change the value, or you add your own velocity model if you want, till you're happy about the theoretical arrival and the match between the theoretical arrival and the waveform. After that, you have a velocity model well calibrated. And you can use this tool to compare your velocity model with the initial contractor's velocity model as a quality check. So what if the well-calibrated velocity model suggests both head wave and direct wave exist? As you can see in this example, here is the source, and because we have a high velocity layer, there is head wave as well as direct wave. And this actually presents a challenge to processors. We have to be consistent. We have to pick the head wave and use the head wave arrival to locate the events, and we have to pick the direct wave and use the direct wave travel time to locate the events. But most of the time we are not sure. We only pick the first arrivals, but it can be a head wave or a direct wave. So the solution that we provide is a 2-point layered model ray tracing. It can include head wave and exclude head wave. All you need to do is check this box to include head wave and uncheck this to only use the direct wave. There are other parameters that you can control. It doesn't have to be a horizontal layer. It can have some dipping angle and a strike angle. You probably also notice this transversal anisotropic layered model options here. As a side note, anisotropy is another factor that will introduce systematic bias into the located events. So if you're in doubt, just include the anisotropy and see what is the differences. And this tool is a very good quality control tool for you to check those scenarios, and you can compare your result with initial contractor's result and see if they have considered those scenarios. So far, let's say we have progressed successfully from leaching to peaking. And soon you're going to realize most of the event has no P wave to peak, and the shear wave is strong, as you can see in this example. And most conventional locating algorithms rely on both P and S wave to locate events, particularly the P wave polarization, to know where the energy is coming from. Without P, most of the locating algorithm will fail. So the solution that we provide is to calculate the source vector using shear wave polarization. And here is the results. If we only use the P wave arrival, we can only locate a handful of events for that stage, which is the blue dots here, a handful, and there's no way to interpret the performance there. And by including the source vector from shear wave, we increase the number of located events by 7 times, and we can easily interpret the fracture network in that stage. So we just have a 20,000 feet overview of the microseismic monitoring processing routine. The real-time processing that we performed in the track actually followed the same routine as the poster processing we performed in the office. It's just in the field, you need to set up the project for every single new stage, and time is critical. So the solution we provide is this Frac Manager tool. It provides you an efficient way to set up a project efficiently. It provides you an expert checklist. As you can see here, start from select the stage, add reference arrays, link shot, etc., etc. Once all these items has been checked, your project is ready to capture the data from the data streams. And if you need to come back and change some parameters, or you need to set up a new project for a new stage, this is a very handy map. So anything beyond processing is interpretation, and we provide a 3D visualization tool to interpret your results. Using one stage as example here, this is a top view from one stage. After we locate a cloud of microseismic events, we fit the majority of the events by ellipsoid, and the geometry attribute is a very good approximation of the fracture network, as well as the stimulated reservoir volume. Actually, this is verified by our forward modeling of hydraulic fracturing in 3DEC. You'll hear more about them in other presentations. The gray lines here are the natural fractures, varies from meters to kilometers. When we inject the fluid into the formation, we will introduce microseismic events. As you can see here, the ellipsoid that include the majority of the microseismic events actually is the first order estimation of the fracture network. So the geometry of the ellipsoid, including lengths, height, widths, top, bottom, azimuths, plunge, and volumes, is a first order estimation of the fracture network as well as the stimulated reservoir volume. So this tool gives you a third opinion about your hydraulic fracturing performance in addition to initial contractors. And here is the final process data looks like. You can see in our 3D visualization tool. So you can see the treatment well path with each state of perforation shot. And the microseismic events are colored by are coded by colors. So different color means it's coming from different stage. We have observation borehole nearby with the sensor distribution. This black line here actually is the gamma ray. So it can indicate which formation that you're performing the treatment. You can actually play back the time and space distribution of the microseismic events, and you can see how the project evolves as well as how the fractures is evolving in this case. And of course, at a location close to the monitoring borehole, we have more events. Far away, we have less events, and we know this actually in the survey optimization status, as you see in the early slides. The other thing is, this is your data. So we're not going to present you only the dots in the box. Each dot, you can actually check the waveforms behind, as you can see in this video. If you, as a quality control, you're not sure if that dot is from a noise or it's a relay signals. So all you need to do is decide, which dot is skeptical, and then you pop up the waveform and check what is the results. As you can see in this video, it has a very clear P wave, has a very clear shear wave, and the peaked event, and it doesn't look like noise. So you have more confidence about the dots, there. So our software is powerful, intelligent. It's also come with a learning curve. So if you want to skip the learning curve, you can contract us for processing as well as real-time processing. We are not going to be another vendor, tell you another story. We're going to present you not only the final processed results, we're going to also present you the processing steps. And each step is transparent, reproducible. So if you want, you can have the software and verify those processing steps if you want. If you do want to be independent and have your own processing power, InSite is on sale, and we provide training and support to get you up to speed. There are many other tools that I don't have time to cover in this presentation, like acquisition license. You don't have to pay for the full license. You pay what you need. Multi-array tools is when you have multiple boreholes doing the monitoring at the same time. We have different tools for different challenges that we didn't cover in this presentation. The good thing is, after this presentation, if you're in the booth, we're going to distribute a free version of InSite, and it's called InSite Viewer. It has all the basic functions, and I'll show you in this video. You can load the data, either processed or raw data. It can import all kinds of data formats, as you see here: SIG-Y, SIG-D2, ESF, basically all the format that is in the market. You can scan through the capture the data events. If they're processed, you will see the first arrival peak. If it's not, you just see the raw waveform. You can see in the move out view or the channel view. If the data is processed, you can use the 3D visualization tool to see what is the time and space distribution of the microseismic events. Here I just highlight the complex object, can be the layer, the formation, as well as the you can hide those formations when you examine the data. And all the processing functions are been disabled, but the interface are there. So if you're interested in any of the processing functions, you just come to talk to us, send us an email, give us a phone call, and we're gonna work out a license for you to check those functions that you're interested in. So thanks to our client that has been with us in the last 10-20 years almost, and to help us improve our service and software. And please stay tuned for other presentations. Thank you for watching this video.